Going on page 36, and we're done. So symmetry of graphs. This is stuff actually you've kind of talked about in maybe a roundabout way a few different times with reflections. You did it in 8th grade math, which you might have taken in 7th grade. You definitely did it in geometry with whether or not it's symmetric with respect to whatever. But right now we're kind of looking at, the first two are looking at reflection symmetry, which is why when we do reflections, we don't just look at how rectangles get reflected and things like that, even though when you're sitting in geometry, we're looking at what actually happens to the coordinates. So if I take this point right here, right, here's my x-axis. This point, if I reflect it in the x-axis, then it reflects down here. So xy becomes x negative y. So when you reflect in the x-axis, your xy looks like this. X stays the same. All that changes is the sign on y. Who can tell me how you read this? What does this little arrow really mean? Starts with an M. It's a strange word to talk about. I mean, it's kind of a strange. Maps to, you remember that? XY maps to x negative y. So every point in the top half of the graph maps to a point that's down here. Okay? So I can either think about like, yeah, this point can, or all these points up here, just reflect down to here, but also if I took this whole thing and just reflected in the x-axis, it's going to look exactly the same because it just flips around, okay? So because of that, if you think about what happens when I reflect in the x-axis, x stays the same, you change the sign on y. That's a simple thing that you don't have to have a ton of things memorized. Remember, all you have to really think about is one point. Okay, I take this point, I'm going to reflect it in the x-axis. Clearly, the x value stays the same, the y changes. It doesn't matter what it doesn't have, even if it's a crazy graph. All you really need is a point to wrap your mind around it, which means that this right here is basically what gets placed in here. So when we're talking about symmetry, right, so since it reflects in the x-axis, it has reflectional symmetry with respect to the x-axis. So for every point that is xy on the graph, x negative y is also on the graph. It's that simple. So once you think that's what's happening, there's an algebra test that goes along with it, and this is kind of leading to what we're doing tomorrow. It's very simple. It's, again, kind of repeating the exact same thing. So for the algebraic test, you replace xy with x negative y. When you do that and you work it out, simplify it, then it should be the same as what you started with. If that happens, it has symmetry with respect to the x-axis. If it doesn't, then it doesn't. Okay? It's that easy. We good? All right, so let's look at y-axis. So if I have a point xy, it's going to map to, right, when I'm going across the y-axis, the y value stays the same because I'm crossing the y-axis. It's the x value that has a sign change, and it's that simple. So if I can reflect every point like that, then it has reflectional symmetry with respect to the y-axis. So for every xy on the graph, then you get negative x, y also on the graph. Which means the algebra test is you replace every ordered pair xy with negative xy, and you should get the same, the equation should be the same in the end. If the equation's not the same, then it doesn't have y-axis symmetry. Okay? We good? All right. I know you're probably thinking, what's the trick here? Because it can't be this easy, but it really is. So origin. Symmetry with respect to the origin. Does this have reflectional symmetry? No. What kind of symmetry does it have? Rotational symmetry. Good. And what's your point of rotation? The origin. Therefore, that's why it's called origin symmetry, right? So here we're not reflecting, we're rotating, okay? And we rotate how many degrees? 180. If I take this and I rotate it 180, you can check by taking your paper. If you can take your paper, turn it completely upside down, it looks exactly the same. You're rotating it 180 degrees. And so this xy here then maps to negative x, negative y. Also, if you remember from geometry, a rotation is a composition of two reflections. Because look what happens here. If I take this and I reflect it in the y-axis, change the sign on x, and then I reflect it in the x-axis, change the sign on y, that's what I get. So basically, this is both of them together. It's like a composition of reflections. Okay, does that make sense? We're just putting it together with functions. Okay, so that means for every xy, there's a negative x, negative y. So the algebra test, you replace xy with negative x, negative y. You should get the equivalent equation. So here's the good news. You're not going to have to do the algebra test, every single algebra test on every single graph. We're going to let you kind of, not assume, but decide by looking at it. Because you can, if you have the graph, which you won't always have the graph, that's also why you need the algebra test. If you have the graph, then you can look at it and, all right, does this have y-axis symmetry? Can I reflect this in the y-axis and it looks exactly the same? No. Does it have x-axis symmetry? No. Does that have origin symmetry? Yes. So we're pretty sure it has origin symmetry, right? But then we have to test it to prove that. So we've got the algebra test and then the description. So in the description, I'm going to go ahead and put origin symmetry because I think that's where I'm going with this. Right? So if it has origin symmetry, then that means that my xy maps to what? Negative x, negative y. Good. Because it's not just one reflection, it's two, so you got both of them. So since that's the case, that means I'm going to take the x and the y here and replace them both with negative x, negative y. So my original is what? Oh, y equals negative 2. Oh, sorry. When I lean on the board, my badge does weird things to the. All right. Negative 2 over x. All right, so this is my original one, right? So now I'm going to take this and I'm going to replace x and y with negative x and negative y. So negative y equals negative 2 over negative x. Everybody with me? All I literally did is I took x and y, changed them to negative x and negative y. I'm not finished, but that's what I did. First step. First step, zero work, you just plug it in. So then I simplify. That means I get negative y equals 2 over x because those negatives cancel out, right? Well, I need to solve for y because I want to see if I can get it to look the same. So to solve for y, I can multiply or divide through by a negative 1, and that's going to give me y equals negative 2 over x. That's what I end up with when I solve for y. Are these the same? Yes. So I'm good. Yes, once you have solved for y and you've simplified everything, they have to look exactly the same. If they do, it actually has the symmetry that you're testing for. If they don't, then it doesn't. Because if you don't have a picture, if I don't have the graph, then I might need to do each one of them. And if I don't know what the parent function looks like, I may need to do each one of them. So then I need to clarify, or it has origin symmetry because, I just was trying to reduce the words. For every xy, there is negative x, negative y. Visually, it's because it rotates 180 degrees. Algebraically, it's because for every xy, there's a negative xy there. We all good? Questions about that? Is this a function? How can you tell by looking? Vertical line test. Is your vertical line test, does it pass that? Yeah, passes your vertical line test, right? Because this gets closer and closer to the y-axis, and so does this. So yeah, this is a function, right? It's a function, and since it has origin symmetry, do you know what kind of function it is? Just a little pop quiz that we're going to talk about it more tomorrow, but all right, think about that. We'll go back to it. Something we talked about. I know it's been a couple years. But. All right, now I want you to look at this graph, and I want you to look at this equation. Do you see anything that doesn't make any sense here? Yeah. X to the fifth, first of all, would x to the fifth have this shape? No. Even if that was not the fifth, what would this do to this graph? Flip it. So this whole thing, I don't have a clue where this came from, because even the person that made this, I was looking back where she got the pictures from. It's almost like I don't know where this one came from, because it's all kinds of wrong. But you should kind of be able to tell by looking. What kind of shape, what is this shape of an x to the fifth graph? What is it similar to? Did y'all talk about those in Algebra 2? Did you talk about cubics? You look at graphs that looks like this, right? Okay, so x cubed, x to the fifth has basically the same shape, just like a quadratic, x to the fourth, they all kind of look the same if you just glance at them. So it should have a shape more like this, but flipped down, and it is shifted down, but is your vertical shift even -3? No. It almost kind of looks like it is, but it's counting by 2. So this whole thing is just bad. So we're going to change that to make it what it should be. So just mark that one out. And it's going to be y equals 0.25 x squared minus 6. That's the equation that actually goes with that graph. All right, so does this look like it has symmetry? Yes, with respect to what? Y-axis. So we're going to put y-axis symmetry because we're pretty sure that's what it has. If that's true, that means that xy maps to, what changes, x or y? X, so this would be negative x, y. I'm going to rewrite my original up here so I can just, it's 0.25 x squared minus 6. Okay, so there's my original one. Then the algebra test is to take this that we can understand easily because you've done this multiple times to understand the concept of the points. And you just replace the xy with the negative xy. So y is still y. That's equal to 0.25, but x changes to negative x squared minus 6. So negative x squared is what? X squared. Okay, I know, this is a hard question. 0.25 x squared minus 6. So once I've plugged it in, that's me replacing these two right here. Then I just simplified it, which is easy. Simplifying doesn't always have to be crazy hard. You get this. Does this match this? Yes. So this works. They're the same. You have shown that it actually has y-axis symmetry. So we can say for every xy, there is negative x, negative x, y. Good? All right. Next one is, oh, let me go back. Is this one here a function? I'm sorry, I went back. This one, if you didn't look back up, I already switched. This one is a function. Is this next one a function? No. Are these notes about functions? No, it's about graphs. So we're just talking about symmetry. Doesn't matter if it's a function or not. So does this look like it has symmetry? Yes. What kind? X-axis. So I'm going to go ahead in my description and say I'm pretty sure it has x-axis symmetry, which means that xy would map to what changes? The y, right? So x negative y. So I'm going to rewrite my original one. X equals y squared minus 3. That's my original. I change x and y, replace them with x and negative y. So x is still x. That's equal to negative y squared minus 3. That's just me plugging it in. Even if you can look at it and you know, because, I mean, this isn't crazy hard to even, just by looking at this, you can figure out that this works, right? But the whole point is that it's an algebra test. It's kind of a proof, so you at least got to plug it in, show that you plugged it in. So that means x equals y squared minus 3 once I clean it up to get it in the same format. Do these match? So those the exact same thing? Yep, they sure are. So that means it has x-axis symmetry for every xy. There is x negative y. Good? All right. Does this look like it has symmetry? Yes. What kind? Origin? Is that it? X-axis? Y-axis? It looks like it's got all of them, right? So this one we have to actually test all of them. So this looks like origin, X-axis, symmetry, and Y-axis. So since I've got to do 3 tests, I'm going to kind of label them as we go. I don't think I'm going to, I'll rewrite my original one. I'll rewrite it here. X squared plus Y squared equals 25. So here's my original one. We'll start with origin, because it was the first one I wrote down. So for origin, XY maps to what? Negative X, negative Y, right? So that means I'm going to replace both of them. That's going to give me negative X squared plus negative Y squared equals 25. So negative X squared is X squared plus negative Y squared is Y squared. It's equal to 25. Does that match this one? Sure does. So we're good. And again, you can probably already realize that once we do the other two, obviously they're going to have to work. But because of that, then we still have to plug it in, because again, it's an algebra test. It's not just a visual thing. So then we'll do the x-axis. So for every xy, that maps to what? X negative y. Good. So that means x stays x. Y becomes negative y equals 25. So that means that I get x squared plus y squared equals 25. That also matches that one. And we're good. And then I also got to do the y-axis, which means that xy is going to map to negative xy. So aren't you glad you don't have to do all 3 on all of them if you know it's not working? So this is going to be negative x squared plus y squared equals 25. So x squared plus y squared equals 25. And it matches also. So those are your algebraic proofs. It's tedious, but tedious doesn't mean difficult. So when it's easy, but it's tedious, at least it's easy, right? Any questions so far? All right, so then we can say, I'm going to write it this way. We're going to put for every this, there is this. Does that make sense? We'll do it. We don't have to do it 10 times. So for origin symmetry, for every xy, there is negative xy, negative y. Oh my gosh. And for every xy, for x-axis, it's x negative y and negative xy. Okay? Questions? Visually, it's easy, right? Even testing it is easy. Just make sure you don't get which one's negative backwards, because even though it's easy, if you're trying to say it as y-axis symmetry and you plug in x negative y here, it's going to make it wrong. So make sure you got the symmetries right in your head, the reflections. We good? Awesome. So go ahead and glue that in. I'm going to give you your assignment, and then I got to mark off part of the instructions because they don't make any sense. And that one's 100% my fault. I have some of y'all stacked up papers. I will come back around and get them. Just make sure they stay there. You get it? You have a question? You sure? Okay, so on the homework, this isn't even and odd functions come tomorrow. I put the wrong title on there. It is Symmetry of Graphs. Even and odd functions is also Symmetry of Graphs, but tomorrow's the extension. And then it says, support the answer numerically, then confirm algebraically. You're not supporting it numerically, you're just confirming it algebraically. Basically, just do what we did on the notes. Okay? Same thing, be able to justify it. You can decide visually and then just use the ones you think it is. Okay, we good? Questions?